Hello and welcome back to another multivariable calculus 3 video. Today we will be talking about tangent planes. So I suppose the first question we need to ask ourselves is, what is a tangent plane? Well, I conveniently have a little drawing here of what exactly a tangent plane is. Well, say we have some surface in the XYZ plane. We want to have this plane right here in blue that is a plane tangent, right? So what we're doing here is we're taking it's perpendicular, right? So we're having a gradient wherein our gradient is perpendicular to our plane. It's a little bit harder to illustrate and explain what it is compared to why we're doing it, and why we're doing it is approximations. Tangent planes are pretty much go hand in hand with our next topic, linear approximations. And why we're doing approximations? Well, approximations are used everywhere, is the simple answer. So that's essentially why we're doing our tangent planes and linear approximations, which is once again something I'll get to in the next video. So how we're doing this? Well, there's a long old proof that I could show you with the little doodle I made up there, but simply our tangent plane is just going to be these two equations here, wherein the bottom one is it multiplied out and the top is it in its simplest form and perhaps the most digestible form for someone learning it. Our equation of our plane is going to be the gradient of f at some point ABC multiplied, or taking the dot product at our vector x minus a, y minus b, z minus c at that point. That is when it is implicitly defined. That is the implicitly defined definition. I will go over what it is explicitly defined later on in the video, but we are only going to be dealing with implicit examples because they're easier, to put it simply. It's perhaps easier to do it explicitly in some scenarios, but my general preference would be to do it implicitly when you can. And like I said, that's this formula on the bottom here. That's just it multiplied out. A little bit ugly, but let's just say that the top is a lot better. That's the general formula that we're going to be using for tangent planes. So let's just go ahead and dive into an example, I guess. So the example states to find an equation of a plane tangent to z is equal to 3x squared minus y cubed plus 2y at the point 103. Well, let's just go ahead and copy and paste our formula that we had up here for our tangent, or our plane tangent. Tangent plane formula. Duplicate you, come down here. Looks good. Well, what's our first step while doing this? Well, let's go ahead and find the gradient at that point 103. Well, what is our gradient? Just to remind us what our gradient is, our gradient is taking the partials of each of our respective variables and plopping it into a vector. So we're going to have a vector comprised of our gradient, or our partial of x, our partial of y, and our partial of z implicitly, which is something that we will transform it into later. Actually, you know what? Let's go ahead and do that right now. Well, what is implicit? Implicit is when our f of x, y, z is equal to 0. So how are we going to make this implicit? Well, let's just go ahead. I'm going to change color for this because this is pretty important. We're just going to go ahead and subtract that z out. So we're just going to have 0 is equal to 3x squared minus y cubed plus 2y minus z. That is it implicitly defined. Not too difficult. All we really have to do is just make it 0 on one side. Obviously, I could have done the other way, but a lot more work algebraically. So now we have our implicitly defined function. Therefore, we can just go ahead and use our formula right there. So what is our gradient of f? Well, let's go ahead and find the aspects of our gradient. So our partial of x is just going to equal, I've been showing the work in depth up until this video. I hope by now that we've had enough experience taking partial derivatives by now, so I am not going to be writing it out all the way. So what is our partial of x? Well, everything else is a constant other than our x variable, so therefore our f sub x is just going to be 6x in this situation. Our partial of y, same concept, but changing the variable to our y. 3x squared, that's going to be 0. Negative y cubed, that's going to be negative 3y squared. Just do a simple power rule there. Plus 2y, take the derivative of that, that's plus 2 minus z. Z is our constant, that's just going to be 0. Let's go ahead and find our final partial of z. We only have 1 in here, so our x and our y's are held constant. We just have negative z. What's the direct, or the partial, what's the derivative, the calculus 1 derivative of our z with respect to z? It's just going to be negative 1. So now we have our gradient, but we're going to go ahead and plug in our point here as stated with our formula for our tangent plane. So our point, it was 1, 0, 3, so let's just go ahead and plug it in. So for our partial of x, we're just going to go ahead and plug in 1. 6 times 1 is just going to equal 6. Same thing with our y. This is going to just be negative 3 times 0. That's going to be 0 plus 2. That's going to be 2. And finally, well, we don't even have a z variable inside of our partial for z, so this is just going to stay the same thing. It's just going to be negative 1. So our gradient at that point ABC is just going to be the vector 6 to negative 1. That is our gradient at our f of ABC. Let's highlight it. We'll highlight it today. There we go. And our x minus a, our other vector, well, that's pretty simple to do. All we're plugging in is our 1, 0, 3 into our a, b, and c. So, I mean, this is just going to be the dot product. Well, let's go ahead and make it we'll call it some vector n. That's going to be x minus a, our a being 1. So we're just going to have x minus 1, y minus 0, y, z minus 3. That's going to be our vector here. Pretty simply, we're just going to take the dot product of these. So our plane equation is going to be 6 to negative 1, taken by the dot product of our vector n, x minus 1, y, z minus 3. Pretty simple algebraically here. 6 times x, 6x, 6 times negative 1, 6x minus 1, or 6x minus 6, I apologize, plus, what is that, 2 times y, 2y, plus negative 1 times z minus 3, that's going to be negative z plus 3. And all this is going to equal 0, just keep in mind. So we have our 0 is equal to 6x. I'm going to group up our variables here to make it prettier to look at. 6x plus 2y minus z. We have negative 6 plus 3. That's going to be negative 3. So that is our tangent plane. That's our equation of a plane, tangent to our given function. Implicitly, we can just go ahead and add that 3 to both sides if we really wanted to. It's not necessary, but we can do it to make it more seem like the calculus 2 equation, something that once again maybe you forgot about up until now, but I'm sure that this equation looks pretty familiar. So we just have 6x plus 2y minus z is equal to 3. That is our equation of a plane tangent to our given function. Pretty simple process. Implicitly, of course, it's pretty simple. Explicitly, could we have done it? For sure. I just question whether or not it would have been more efficient because, well, what would we have had to do? Let's go ahead and go down here to our explicit definition. I pre-wrote it out because these are the two things I really want you to take away from this video. Perhaps you may not have grasped exactly what a tangent plane is or why we're doing it, but at the very least you should understand how. Maybe not the best way to think about it, but hey, you got to do what you got to do on an exam, right? So explicitly, our equation for this is just going to be z is equal to our partial of x at AB times x minus a plus our partial of y at the point AB times y minus b plus our f of AB. That's going to be explicitly defined function. Implicitly, exactly what I did here, a little bit more digestible in my opinion. We have our gradient of f at ABC, taking the dot product of our x minus a, y minus b, z minus c. Explicitly, I'm sure if we did it, it would have given us the exact same answer. Of course, it would be instead, what would that, z is equal to 6x plus 2y minus 3. Not going to show that because we already did it implicitly, so there's really no point other than perhaps checking our work could be something that the explicit definition could be helpful with, but beyond that, I see no point why we don't just do it implicitly every time. As I said prior, that's just the way that I like it. That is tangent planes. In the next video, we are going to be going over linear approximations, something that these two go hand in hand essentially. So thank you very much.